Hello, everybody, and welcome to another wonderful day of sophomore seminar. So today we're going to be taking a little bit of time to talk about the scientific literature, because as you try and get into the sciences, you're going to notice that it turns out the literature is quite big. There's a lot of papers out there with a lot of good information. So I kind of want to teach you the basic skills of how to sift through it for what you're looking for. So one of the biggest things that I do like to emphasize is that when we're talking about scientific progress, it's almost always based on first establishing a good knowledge of what has already been done. As Einstein said, if I see far, it's only because I stand on the shoulders of giants. So, in order to know where you're going to proceed with experiments, you first need to do a thorough uh, examination of the literature. And there are several key places that you can start. The most common of which, and pretty much the bedrock of all scientific knowledge, is the peer reviewed scientific papers. So we'll be talking about this a lot, but when people talk about scientific articles, this is what they're talking about. It's papers that have been written by scientists and reviewed by scientists. And this peer review process should help encourage that all of the findings are fairly accurate. Uh, and as long as they end up eventually being replicated, should be golden. Another fairly common but less talked about place to obtain knowledge is oral communications. So these are going to be things like talks and poster sessions. And a lot of times you're going to find research that's in progress, so more cutting edge, as well as it can be a good way to get a more general overview on some things that aren't always addressed in scientific papers. So this is one of the reasons why you'll always hear all of your chemistry faculty asking you, begging you to attend all of the speakers that we bring in. They're a really good source of information and to kind of get an idea of what's going on out there. Also fairly helpful is scientific books and textbooks. So this can be anything from a pop sci art book to something that's actually, a good old textbook. But this can also include things like scientific old books of scientific data. So one of my personal favorites is the CRC handbook. This was originally produced by the Chemical Rubber Company, and it's essentially a giant book of physical properties. So these can be really useful, but they often kind of help fill in the gaps of the scientific papers. But also in that same um, same general view, you also have various scientific databases. So this can be so there's a lot of groups out there that essentially try and put together almost this sort of peer-reviewed data set. So this tends to be a lot of physical data or data of physical properties. So this can be anything from the National Institutes of Standard Science and Technology, or NIST, which is famous um, for providing detailed chemical info. So if you're looking for things like boiling points, masses, or hazard info, this can be a good place to go. You also, if you're working with crystallographic data, so if you're looking for structural information, this is especially useful in biochem. The Cambridge Crystallography Data Center is a really good source. If you're looking for good physical data, so again, things like boiling points, vapor pressure curves, I often use Dortmund Data Bank myself. So this is actually instituted by, again, a chemical company working alongside universities in Germany. And it's a really good source for a lot of chemical engineering or physical chemistry data. Now, also useful to note that's out there is crowdsourced resources. So I like to think of crowdsourced resources as a good place to start to get a general view of a topic. So this can be things like Wikipedia or ChemLibre. They're often fairly accurate, but not trustworthy enough to cite. So a good way to use things like Wikipedia is you'll go ahead and read the Wikipedia webpage to get a general overview, and then you go to the citations, because the citations should be of these more rigorous resources like scientific papers, like scientific books. So this can be a good place to start, but it should only be a place to start, and you should never use them in your citations. So let's go ahead and talk about that backbone of the scientific literature. That's that peer-reviewed article. So one of the defining features of a peer-reviewed article is that it's been approved by at least 2 other scientists. In practice, this is usually 3 or more, and you'll often have peer review committees that will be up to 10 people. So with more eyes on a paper, this should be a good way to make sure that whatever's in it actually is up to snuff. Now, the problem is that peer reviewed is kind of a broad category. So we often try and break up peer review papers into 4 major types, and they're often labeled as such in the literature. The first of which is a review article. So a review article is essentially a summary of the state of the art in some type of scientific subfield. So this can be anything from dicopper complexes, or photosystem 2, or water oxidation catalysts, or tin surfaces, or a specific protein. But it's often a fairly narrow topic that is that usually summarizes years worth of work. So if you're trying to get in, trying to learn a field, this is a good place to go. Try and hunt down some review articles. Also, one of the beautiful parts of review articles is all of the citations. If you're looking for good citations or good papers for specific details, I love what I refer to as citation mining. You find a good review article and you find the most interesting facts and look for where they came from. It's worth noting these are called a secondary resource because there is no direct research in them. They're more a summary or a secondary look at the science. Now, one of the other things that's worth noting about review articles is they typically are fairly big. So pretty much review articles start at about 20 pages. I have seen several review articles that go over 100 pages. These things can be quite significant depending on the topic being looked at. Now, if we go into the primary literature or papers that are doing direct research, the workhorse of these is going to be the scientific journal. These are typically 5 to 20 pages, and they're essentially full details of a single either discovery or class of discoveries. So a single scientific project. And it should essentially have full details of how the discovery was made and all of the consequences of its findings. So it should give you a good general overview of the question, what was done, and what it means. So these are good places to start when looking for scientific information. However, it does actually take a while to produce a journal article. It is not uncommon for it to take over a year to do the research and a year for it to go through the review process. So if you want your scientific findings to come out a little bit faster because you think you have something important, you'll typically write a communication. So these are essentially a brief summary of some sort of research project with a brief summary of how the experiment was done and what the results were. And as a result, they tend to be a little bit more important, a little bit more flashy, and a lot shorter. These typically start at about 2 pages. It's rare to find a communication that's much more than 5 pages. So they're nice short reads, but again, fairly cool. Now, one of the things that's worth noting is because they are so brief, they often don't have a lot of experimental information. However, it has become popular that that information will be available on the journal website under what's called supplemental information. So if you really want to know how work inside of a communication was done, make sure to check out the supplemental information on the publisher's website. Now, that can be a little bit tricky to find, but it's fairly useful. Now, a little bit of an unusual type of publication that used to be fairly popular, but it's kind of going out of vogue, is the monograph. So essentially, a monograph is a series of scientific articles, all in the same general work, often done by several research groups in close collaboration that go over a single topic. I've actually seen several on one of my previous projects of water oxidation. Now, one of the things that's worth noting is that these kind of had their original debut as essentially being published as a long manual or a short book. And occasionally they're still done. But there are several journals out there that still publish monographs. But again, not as popular these days, and you won't see them quite as much. So let's go ahead and kind of view in on these major primary articles. So primary forms of publication, the communication and the journal article. Most of these are written in the same general format. You can break them down into several key parts. Now, if you're just trying to get a good general overview of the scientific literature, you don't always have to read the whole article. There's a couple key bits, each of which can be useful in its own way. So a part of the paper which a lot of people don't put enough thought into is the title. So it's worth noting that if you're trying to decide whether or not a paper looks cool, usually you don't get past the title. So if you have a good scientific paper title should let the reader know what the topic is, what it um, what the general thrust of the research is, and often it's fairly important to let the reader know what approach is being used. Are you using a computational study? Are you using NMR? Are you using IR? Depending on what the methodology is used, you can drastically shift your readership. So an overview of the topic, often what sub aspect you're looking at, and the approach being used are really important when trying to craft a good paper title. Then another really important feature is the abstract. So if the title catches your attention, you'll often look at the abstract, which is more or less a single paragraph summary of the entire paper. So it is brief beyond the point of usefulness, because you need to quickly summarize what the general topic being studied is, why it's important, what approach was being used, the key findings, and what they mean. So usually something kind of falls between the cracks, but it should give you as the reader a good idea of, is this paper worth reading? So if you do that, you're going to get into the bulk center of the paper. So a good paper is essentially constructed like an hourglass. You start with some broad general topic, say something like, we're looking at trying to minimize global climate change impacts. So I'm going to do this by a specific subtopic of green energy. Now, one of the failings of green energy is X. So I often look at energy storage. Current state of the art is some subfield, but we're going to try and improve it by looking at blank using blank approach. That should be the general thrust of the introduction. So as a result, if you're interested in getting a general overview of a topic and trying to figure out what a given field is about, you often don't need to go past the introduction. However, if you're trying to figure out where the shortcomings of knowledge is, introduction is often good, but that's kind of the most that you often get out of the introduction of the paper. However, if you look at the abstract and you think that something might be useful, but you're not sure, you can always take a look at the introduction, figure out what the specific question is and what approach they're using, which is usually located in the last paragraph of the introduction. So if you want to jump straight to that question, jump straight to the last paragraph of the intro, and you should have a good general idea. From there, you go to the experimental section. So if you're just trying to get a general overview of the literature, usually you skip over the experimental section, but it should always be present, because if you're trying to replicate a paper, this is where you're going to spend most of your time. So if you're a casual reader, you're going to be spending a lot more time reading the introduction. If you're in the subfield, the experimental section is usually your bread and butter and what you're spending most of your time with. Now, one of the things, again, as I said previously, if you're looking at a scientific communication, a lot of the information in the experimental section may have been moved out to the supplemental information on the publisher's website. So from there, we go to the results. This is your good technical details of the experimental study, what exactly was found, sometimes what it means. Because part of the problem is that the discussion is usually trying to focus on the meaning of your scientific findings and how it connects to the greater scientific framework. But there is a slight problem. in that every journal does this a little bit differently. In most chemical journals, results and discussions are written together, so you can't really disentangle these two. Most biological journals do a results section and then a discussion section. So if you're trying to find greater meanings and connections, and you're in a bio paper, jump straight to the discussions. If you're reading a chemistry journal, you're going to have to wade through the results and the discussion. Usually, you're going to have a series of graphs or figures, after which you're going to have a summary of what they mean. But if you're interested in the greater field or connections, you're going to jump to the end of that paragraph to find the discussion, because it will be embedded in between those graphs. Now, again, a little bit messy, you have the conclusions. So this is a summary of the key take-home points. Most papers will have at least one paragraph dedicated to this. But again, especially in bio papers, conclusions and discussions are often blended together. However, in chemistry journals, conclusions usually is its own separate section, usually not more than a paragraph or two, sitting there right at the end. And again, these sections do have a tendency to bleed together a little bit more in a communication due to the extent of the brevity, where everything can become a little bit mingled. But this is really useful to kind of figure out where you should be spending your time if you're reading a paper. If you're a casual reader, you're usually not getting much past the abstract, the introduction, and the discussion and conclusions. If you're in the field, usually most of your time is spent on those nitty-gritty details and the experimental and the results. However, this is what you do if you find a paper. But where can I go to find papers? Well, there is a huge array of scientific journals out there. There are hundreds of greater journals, and in chemistry alone, there are dozens of good journals. But in general, scientific journals are often broken down into tiers. So the top tier journals are almost shared by every scientific discipline, and every scientist worth their PhD wants to be in one of these journals. So the top three are traditionally Nature, Science, and PNAS, or Proceedings of the National Academy of Sciences. Everybody wants to be published in these three journals. If you want to get a good idea of general scientific information, read these on a weekly basis. All of them are essentially published every week, and they do a good overview of the best of happening in science. And they often do a weekly summary of all the other journals. So one step down from these top tier, but often still considered top tier, are usually journals dedicated to an entire subfield. So in chemistry, my two favorite are the Journal of the American Chemical Society, or JACS, based out of the US, and Angewandte Chemie in Germany. These two deal with almost all of chemical fields, and there's a bit of there for everybody. But they also publish at a much faster rate, and they let in essentially things that aren't groundbreaking, but are still important. Now, alongside these, you often have little subcategory journals published by these top tier. You have Nature Communications or Nature Chemistry, which are right up here with Angewandte Chemie and JACS. However, if you're interested in a specific subfield, you might want to go ahead and hunt down if there's a journal for your subfield, whether it's biochemistry, inorganic chemistry, or maybe you're looking for a good chemical review. ChemRevs is a great source, or Chem Communications for a constant stream of updated research. Once we get into here, there's hundreds of really good journals out there. And so it's hard to try and figure out what's the best source unless you talk with somebody in the field and they'll tell you who their favorites are. And again, everybody has them. But this is often going to be dependent on what your area of interest is. So if you're looking for a good journal to look at, feel free to ask me or any of your other professors. We are definitely going to have our opinions, and you might need to tell us to shut up at some point because we get a little nerdy about it. So with all of these journals out there, we need a good way to try and winnow through and find the articles we care about. And lo and behold, in the age of scientific progress, we need a search engine. So there's several good search engines to go out there. A good overview of some of the ones available. You can go to the Truman Library Resources. There is a specific subtag for chemistry, which will give you good information on what journals the library has, and some good search engines to use. So some of my personal favorites that are pretty good in general overview includes Google Scholar. So you have Google for general research. You can always go to Google Scholar to essentially win out all the dross, all those crazies on the internet, and go straight for scientific articles. So it uses essentially the good Google search engines, but now it's tailored just for scientific articles. It's a pretty good resource. It's not great, but no matter what your scientific discipline is, you can use Google Scholar. If you're interested in good biological research, a good resource is PubMed. This is run by the NIH, and it's a really good general resource. However, I'm a chemist. I'm a little biased. There is actually a specific search engine out there just for looking at the chemistry literature, and that's going to be SciFinder. It's essentially run by the ACS, and it's tailored just for chemists. So this does mean it is still pretty good if we're looking at chemical adjacent fields, including quite a degree of biology, all the way onto ecological perspectives, and over into things like physics and geology. But it does have some useful talents that you aren't going to get out of a non-chemistry search engine. It is worth noting, though, that you do need to have a license to use it. Thankfully, as a Truman student, you can actually get an account through the Truman license to access SciFinder at this link. And I'm going to ask that you do so before class so that we can go ahead and play around with SciFinder in class. Now, some of the useful features of SciFinder, some that are actually shared by other journals, are things like you can go ahead and if you know an author you're interested, you can go ahead and search for that author and then further refine that search by what other authors they worked with or whatever journals they published. If you know that, there's a professor or a researcher who does really interesting research and you're pretty sure they put a good article in Science, you can go ahead and say, look for this author in Science. You want to have fun? Go ahead, search my name for Winnicott in Science, and you'll actually find something. Also, much more useful for us is usually looking at specific topics. So if you're interested in, say, something about water oxidation or about protein aggregation, you can go ahead and put those topics in there and even add further refining keywords. And it's actually a really good resource, much better than I make it sound. But something that is very unique about SciFinder that you might find very useful in your lab classes is you can actually search by chemical structure. So it has a tool where you can draw in a chemical structure and look for that specific molecule. And if nothing else, if you're trying to figure out the name of a molecule, draw it in SciFinder and go ahead and search. It will give you the technical name of both that molecule and any closely related ones. I've even made use of that myself a couple times for very complicated molecules. So now you've got a basic overview of the scientific literature. You can go out and find an article that interests you for our later assignment. Till then, take care.